All right, algebra 2, let's take a look at our next example here. Example 5 says factor 4x squared plus 4x minus 15 completely. So we go through the same process we did up here. Is there a GCF involved? So let's check 4, 4. Yeah, those would have one, but doesn't have it in common with 15. Nope, no numbers can come out. Let's check x's. We have x squared, x, and then nothing, so no, we can't take x's out. So no GCF coming out. Is there a pattern? Well, remember we have to have square root things here and here. So 4, yeah, square root of 4 is 2. 15, square root of 15, no pattern. And so finally that leaves us with just guess and check. So that's what we're going to have to do. Now it is a quadratic trinomial, so that's going to factor into two binomials. So we can go ahead and set it up. Okay. I always like to, and I always remember FOIL here. I always try to do my first. So how do I get my first term here? Well, those would be my first terms in here. So what are the factors of 4? Well, you can use 1 and 4. You can use 2 and 2. I don't like to use 1 in anything. It does work sometimes, but it's a little more rare. So I'm going to actually use 2x and 2x. And the first terms always have to have x's with them. Okay? So we got that. Then I go to my last. How do I get my last term? Well, we get our last term by our last terms in here. So first things first, our last term is negative. So how do I get a negative with multiplication? Well, a positive times a positive wouldn't work because that would give us a positive. A positive times a negative, now that would give us a negative. So one of them is going to be plus and one of them is going to be minus. You don't know that the plus is first and the minus is second, but we got to start somewhere. So let's plug it in as such. And we know they're not both negative because the negative times the negative will give us a positive. So it has to be alternating signs. And then we have to start thinking of the factors of 15. So we have 1 and 15, 3 and 5. Again, I don't like 1 and stuff, so I'm going to start with 3 and 5. And then let's just put 3 here and 5 here. Now, I don't know that that's the answer. That's the whole guessing part. So now we're going to check it to see if it actually works out. So let's FOIL this out. 2x times 2x is 4x squared. 2x times a negative 5 is a negative 10x. 3 times 2x is a positive 6x. And then 3 times a negative 5 is a negative 15. So we check this middle term, see if it works out. So 4x squared minus 10x plus 6x is a negative 4x minus 15. And is this what we started with? Oh, gosh, it's so close except for this little guy here. This positive, or this negative sign should be a positive. So if that's the case, if you have the exact number that you're supposed to have, but the signs are just wrong, then all you really have to do is flip your signs in here. So I'm going to go ahead and make this one a negative. So let's get my eraser out. This is why we always use pencil in math, because sometimes we have to erase. So this one was positive. I'm going to make it negative, and then this one will then be positive. So what does that change down here? Well, I like to start fresh. I'm not going to use that. Oh, sorry. I guess I shouldn't scribble. Let's erase. All right, let's erase all this and FOIL it again. All right, and you're going to get good to the point where you can mentally FOIL it out, but for now, since we're new at this, let's actually physically write it down. So 2x times 2x is 4x squared. 2x times a positive 5 is a positive 10x. Negative 3 times 2x is a negative 6x. And then negative 3 times positive 5 is a negative 15. So let's combine 4x squared and 10x minus 6x. Bada boom, bada bang. We have plus 4x minus 15. Yay! So it checks because now we have exactly what's up here. Therefore, this is our official answer here. And we know it works because we checked it, and we're good. Next definition is what we call prime. Now, you know what a prime number is. And a prime number, you know, they start with 2, then it's 3, then it's 5, then it's 7, then it's 11, etc., etc. It goes on forever. Prime numbers don't have any factors, no factors, other than 1 and itself. Okay, so that's what makes a prime number. So that's essentially what a prime polynomial is. A polynomial who cannot be factored, no factors, into polynomials of lower degree whose coefficients are rational numbers. So let's just throw an example out there. Let's say we had 3x squared minus 17. Well, there's nothing in common between 3 and 17. There's no x's I can take out. This is definitely not a special pattern because I have square root of 17 and the square root of 3, neither of which are perfect squares. Let's see, it's not a quadratic trinomial. I can't factor it into binomials. So this guy would indeed be a prime polynomial, okay? So it's kind of the same idea. You can't factor it into stuff as it is with the numbers. Okay, so let's see how that's actually used. Example 6. Letter A says, is x squared minus 6 prime over the set of rational numbers? Now remember, if you remember what rational numbers are, those are decimals that repeat or stop, okay? If they don't repeat or they don't stop, then they're irrational numbers. Now, our most famous irrational number is pi, or remember E we learned was a new one. So those are good examples of things that don't have a pattern, there's no repetition, and they never end. So that's what we mean by rational would be, not those numbers. So essentially we want to say, okay, is this prime or does it factor? We have to see. So there's nothing I can pull out as far as the GCF goes. This actually might fit one of our special patterns. The one I'm thinking of is a squared minus b squared. And we know that that factors into a plus b, a minus b. But, so we take the square root of x squared, and we get x. We take the square root of 6, though. I'm not thinking that that's going to be a rational number. So let's just try it. Oh, look, I just did it. Square root of 6 is 2.4494897743, and I can guarantee you it does not stop there. That's just where our calculator screen ends. So this guy is going to be an irrational number if I try to take the square root of it. And so therefore, is it prime over the rational numbers? Well, if I can't use a rational number to factor it, then yeah, it is going to be prime, because the square root of 6 is irrational. Okay, so this guy is prime over the rational numbers. Okay, so it is prime over the rational because I can't factor it into rational numbers. Okay, and in fact, if you try to take the square root of anything that's not a perfect square, it is known that it is just going to be an irrational number every single time. So if this is anything that's not a perfect square, 24, 32, all of those are going to be irrational. Okay, so part B, though, says, is x squared minus 6 prime over the set of real numbers, and the real numbers extend it to the rational and the irrational. So now that we're allowed to use irrational numbers, which is what we're going to get here, well, yeah, we can actually factor it. So no, it's not prime, because it will now factor into our pattern here. Okay, so we would say, okay, it factors into x plus 6, or not 6, the square root of 6, and x minus the square root of 6. That would actually be what it factors into. Now, of course, we should always check this. So let's boil this out. X times x is x squared. X times the negative square root of 6 is a negative x square root of 6. X times a positive square root of 6 is a positive x square root of 6. And then the square root of 6 times the square root of 6, well, of course, it's going to be negative. But the square root of 6 times the square root of 6 is actually just 6. What happens with these two middle terms? Well, one's positive and one's negative, and they're the exact same, so they cancel. So we get x squared minus 6 out, which is what we started with, so we know that we factored it properly. So this is prime over the rational numbers, but if we're going to the reals, which include irrational, it's not prime because now I can actually make factors with it. Now, I have another example for you which has a lot of factoring in it, so I certainly hope you join me for the next video.